Harry will be talking about geology and absolute model ages of the same region, Rima Bode region, a candidate for future lunar landing site. The stage is yours, Harry.
Okay, so there we go. So yeah, my pleasure talking about the geology and some absolute model ages of the Rima Bode region as a candidate for future lunar landing site. And as you can see, I'm representing a larger team. All of those folks contributed with their brains to this study, and it's really appreciated. Next, please. Okay, so all of you know that there's currently a really huge interest in returning to the moon. So several nations, including the US, China, Russia, and so forth, and Japan, have voiced their interest in returning to the moon, and Europe is, of course, part of this endeavor. In terms of ESA and Europe, there will be a very important conference in September of this year. That's the Ministerial Conference, which is very important for the decision-making of ESA in terms of budget and strategy. And sort of in preparation of this Ministerial Conference, ESA was putting together several topical teams that study different traits of lunar research. You know, one is dealing with lunar geology, another one polar science, geophysics, skylights, and so forth. You know, and ESA also issued a call for ideas, which we responded. And our idea was basically to use the large lunar lander that is planned to basically support humans on the surface. It's a cargo lander, if you will, that brings goods for astronauts to the surface, but can also be used as a scientific lander. You know, it's a very capable, very large lander, bringing about 1.8 metric tons to the lunar surface. And of course, you can imagine what you can do with 1.8 tons of scientific experiments on the lunar surface. And so our idea was to utilize this lander and, for example, add on top of the lander 100 to 200 kilogram class rover that, in our opinion, should have some night survival capabilities. We are also thinking about a modular approach. So I'm comparing this to shipping containers, because this large lunar lander is supposed to basically go to the moon every 2 years or so. And so it's simply necessary to have this modular approach that you can maintain this cadence and also lower costs. So in a sense, you're just having compartments there. We can switch in and out different instruments. That's at least my idea. We're planning at the moment for some in situ observations. However, that could be easily turned into a sample return mission with 1.8 tons. You know, that should be possible. Now, of course, right now there is a lot of interest, and Ian was just referring to going to the moon and going specifically to the poles. Now, we were sort of shying away from the poles because there are several really other interesting parts of the moon that you can investigate. And so we were looking for a simple landing site, you know. So nevertheless, it should have a high scientific potential and should, in an ideal case, help answering multiple questions. So that limited ourselves to the near site. So we don't need a relay satellite. We have direct communication. We wanted to have a safe landing site. And of course, we want to do excellent science in terms of different research topics on the moon. So volcanism, impact processes, tectonism, all these things, you know, should be accomplished at one landing site. And so the Rima Bode landing site, of course, is not completely new. It has already been a constellation site. And so that's why we got attracted to that. Next, please. So in the next slide, you see a sort of a regional map. Sasha already introduced you to the area of interest, and I would just want to point out that it's a really interesting area. First of all, you see the dark area consisting of pyroclastic deposits, but then you are also close to the rim of the Imbrium Basin. So you certainly get material from this basin to the landing site, but then you also see Eratosthenes and Copernicus, which are two other very important chronological markers. And so again, from these two craters, we expect to find material at the landing site, which would allow us to basically, or hopefully, date the Imbrium event, the Eratosthenes event, as well as the Copernicus event. Next, please. So if you zoom in into this red box, you see very complex geology, and Sasha was already alluding to that. So I'm just pointing out that you have this different mare basalts, and I will show you this in the map again. You have the very dark mantle deposits. In the east, you see the Imbrium sculpture, and in the north, you're moving towards the Apennine Bench region, the Apennine Mountains. Yeah, if you look at the geologic map, next, please. And Sasha was already presenting this, so I can be very quick. It's just emphasizing a very complex geology, and that really is attractive to us. At the same time, we have a very safe landing site, as I will show in just a second. So that's all playing in our favor. Next, please. Okay, so talking about the ages. So we started out putting down map areas based on our geologic map. And if you look, for example, the area CR1, which is right on top of the ray from Copernicus, we dated it to be 3.45 billion years. Now that's obviously much, much older than Copernicus, the 800 million years that we think Copernicus is old, So in our interpretation, there's just a little bit of material from Copernicus covering the mare basalts, but the material was not sufficiently thick to modify our crater counts. So in a sense, the 3.45 billion years, most likely the age of an underlying basalt. In the north of it, we have a larger count area that shows a 3.7 billion year model age with some indication of a resurfacing event at about 2.5 billion years. In the south, we also have two areas that we dated to be at about 3.3 billion years. And then in the north, some younger basalts that are also topographically lower at about 3 billion years. Now, when it comes to the dark mantle deposit, to the pyroclastic deposits, this area D1 shows an age of about 3.7 billion years. But from a point of view in morphology, it's clear that the mare basalts are a little younger. They are embaying the pyroclastic deposits, so that's consistent with our crater counts. The count area in the south shows two ages, most likely an older age dating the highlands basically, and some resurfacing event. The area in the east, D3, we did not get reliable ages, so that's something that we need to refine, do again basically. And also C1 sort of causes problems because on the small surface area that we have, all the craters are in equilibrium, larger craters than 800 meters. So that tells us that the crater is at least 3.8 billion years old. On the other hand, it's superposed on the ejecta material of Imbrium, so that would give it an age younger than about 3.92 billion years. Next, please. So let's see what we can do when we land there. So here's just a landing site in the center, the big white dot, if you will, and some nominal traverses to interesting things. If you go to 1, you could sample the pyroclastic deposits. 2, you would have access to a fresh crater, and you could also see the wall of the bigger crater. In 3, you could sample some high titanium classy pyroclastics. 4, you have a dome structure. 5, you would have access to plagioclase and some highland material. 6, you would sample the Copernicus material. 7, you would have some medium titanium basalts. 8, you would cross the wrinkle ridge and you could get the structure of the wrinkle ridge. And finally, you would have access at 9 to Bode C, a very young crater. Next, please. And along the traverses, of course, you can have multiple stops. So instead of the spider diagram, here we have a sort of a loop. It's about 180 kilometers, and it would take about a year 2 years to basically get around here, 176 kilometers. And as you can see, you can stop, of course, multiple times. I just want to introduce you or show you stop 4, 8, and 9. Next, please. So at 4, you would be investigating this cone-like structure. It might just be a highland hill with a crater on top of it, but it could also be a volcanic structure. And you can see some linear arrangements, could be some inflated lava basalts or some landslide that caused this linear arrangements. And then you have, of course, access to fresh craters, a crater at the south that sort of is half covered with material from the cone, and also some very old irregular shaped craters that can be investigated. Next, please. Then when we go across the wrinkle ridge, again, we have, of course, access to the wrinkle ridge and can look at the structure there, but also many impact craters that have different morphologies and different ages. Next, please. And then Bode C would have access to the rim of the crater, so the steepness of the wall is, or the ejecta is not something of concern. We can easily drive up there, and there we would have access to some boulders, and would also have a peak basically down on the crater floor. Next, please. Okay, in terms of composition, that's the Clementine color ratio. You see the different colors. Clearly the pyroclastic deposits show up at these dark purple units, and then the basalts in various tones of blue and orange and green. And then again, Bode C is a very young crater showing fresh material basically exposed at the surface. Next, please. In terms of landing site safety, you're sort of located on this bench between the higher terrain of the Apennine Mountains and the from our region and the lower basalts in Sinus Estum. But as you can see, topography-wise, there's not a lot of elevations that need to be covered. Next, please. We can use, of course, the data to look at some slope maps. And as you can see, the entire area has benign slopes. Even if you go up to Bode C or across the wrinkle ridge, you would not encounter slopes that are much steeper than 7 degrees, and that should be feasible for a rover. Next, please. In terms of rock abundance, also very safe unless you get too close to these fresh impact craters that have, of course, some boulders on it. But that's, of course, also a chance. You can go up there and sample these boulders. So, but the landing site itself is fairly free of rocks, and so most of the traverse. Next, please. Okay, so what would we like to do? This is just a very wordy slide. I apologize for that, but of course, we are interested in the geology, so the geologic context, the samples, of course, that we can investigate. We can date, or at least try to date these samples in situ. Now, that's an interesting endeavor, of course. And of course, we can do some geochemical and mineralogical and physical analysis along the traverses. When it comes to geophysics, I would be interested particularly in the subsurface along the traverses. So for that reason, I would like to operate a ground penetrating radar continuously with the rover driving across the wrinkle ridge, for example, or we could do some measurements on the lander that requires more time, like heat flow and seismometers and magnetometers. These pyroclastic deposits are, of course, very, very favorable for in situ research utilization. So we could test different techniques. And finally, with the lander, we could also try to characterize the lunar environment, radiation doses, temperature, dust collection, all these things, but also determine the orbital parameters with the laser reflector, libration, Earth-Moon distance, and so forth. And eventually then, if the mission is selected at one of the later mission slots, we could also think about sample return. So with the next slide, I come to the conclusions. Okay, so I think Rima Bode is really super interesting because it allows us to do many, many different things. We have a very complex geology. Our preliminary map showed that, and so we have access to several more units. We have access to pyroclastics, we have access to impact craters, as well as basin deposits. All of them have different ages. The landing site, at least as far as we know by now, is safe for both either robots or humans. And I think particularly the ISRU feasibility is also a great benefit of this landing site. Okay. Yeah, with that I stop. Thank you very much.